Welcome my friends, welcome to my next lecture. Now in my last lecture I was talking about I have defined the notions of harmonic functions and I have explained how to calculate given a harmonic functions the harmonic conjugate, how to calculate harmonic conjugate of a given harmonic functions, and then I was discussing about what is called some properties of harmonic functions. So my plan for today's lecture is to just finish this couple of properties, not of course all. I'll have kind of selected few properties of harmonic functions. So I will complete those properties and then I'll move what is called singular points. So analytic at a point so then I'll talk about the singular points, and then I said that I'll talk about what is called multi-valued functions and branch. Maybe I think in next week I think I should start with what is called multi-valued functions and what is called branch. So my plan for today's lecture is to just complete couple of properties more about harmonic functions and talk about what is called singular points. Okay, so as I said, so I just start with, again, just recall those kind of things I have already explained. So like suppose if I have a function f which is u plus iv, which is analytic in some domain given, then I have explained if suppose u is given, suppose if I have f is equal to u plus iv, and suppose the expression of u is given, then how to get the expression of v, or in other words how to get the expression of f. Then this first one I have already explained, given u how to calculate the expression of v, and in other words how to calculate the expression of f. That it means given harmonic functions how to find the harmonic conjugate, that means v, and how to get the f. So this portion I have already done. Then the same way I can ask the question, suppose you have f is equal to u plus iv, and now suppose instead of expression of u, suppose expression of v is given, okay, then how to get the expression of f? That means you have to get the expression of u and then you have to get the expression of f, and that is also possible. I have already explained, because this time you have f is equal to u plus iv is given. So now this time expression of v is given, I have to find the expression of u. Then what is the procedure? So again, so if you want to just kind of say that I know the one process where u is given and I know how to find v, then make in that situation. So that light heated by minus I is a constant. So what it turns out is that this is v minus I times u. Now it is okay, right? Now if f is analytic, so therefore minus I times f, it's also analytic functions whose real part is given. So how to calculate the imaginary part u, that you know. So just you have to use the CR equations, solve partial differential equations, then you have the expression of u, then at the end you have the expression of u and v, then you have the expression of what is called f. Okay, so then third and fourth little tricky. So it says that suppose you have a function f which is u plus iv, and suppose instead of having the expression of u and v explicitly, suppose you have the expression of u plus v or u minus v, then how to get the expression of u and v separately. So there also you need a trick. What kind of trick? I already explained. So this says that, okay, instead of dealing with the functions f, you have to deal with some constant multiple of f. That means if f is equal to u plus iv, okay, so then I suppose u plus v, this expression is given, then what should I do? So then you can say that I already told you, so you consider this kind of functions, 1 plus I times f, and what is that? This is u plus iv, okay, maybe I think 1 minus I, just write it 1 minus I. So what is that u plus iv? Then you will have I times, so that means minus iu and then I square b, okay, so okay, now I think leave it this one. So f is there, okay, fine, f is there. So now what is I time minus I times f? This should be, I have already explained. So this should be, you have minus iu plus v, right? Okay. So now if I add it, then what is happening? See, f minus if, this should be u plus v, okay, and then if I take I common, this should be v minus u, right? Now look at the left hand side. So left hand side f is analytic given, right? So f is analytic, I times f, that is also analytic functions. Then I am subtracting f minus I times f, that is also analytic functions. So left hand side is an analytic functions whose real part is u plus v and imaginary part is v minus u. But you know, given analytic functions, if you know the real part, then how to calculate the imaginary part. So therefore this is known, so therefore you know how to calculate v minus u. So therefore you have the expression of u plus v, known expression. Then using Cauchy-Riemann equations, then you have the expression of v minus u. So you have something, then if you add it, If I add it, then this get cancelled, so you have the expression of V explicitly, and then similarly you have the expression of U explicitly. So that means instead of instead of having the explicit expression of U and V separately, if I have the expression of say U plus V or U minus V, and then how to get the expression of U and V separately. So instead of dealing with F, so for example what I am dealing in here, 1 minus I times F, this kind of functions I am dealing. Okay, so that means instead of dealing with the functions F, you have to deal with some appropriate scalar multiplications of F, so that you have to somehow guess. So if I take these scalar multiplications, and then if I look at the either real part or imaginary part, and then see that the real part or imaginary part and the expression what is given in your questions that is given, that means you can have the other expressions, and then do some algebra, you will have the expression of F separately. So that is couple of problems. So you can expect this kind of problems in your assignment or exam as well. So these are the kind of couple of things I have discussed. So that means, so in the problem maybe I will give some kind of combinations of U and V as a given expression, and then I will ask you, okay, find the expression of F. That means you have to find the expression of U and V separately, and then if I add it, then you have the expression of F separately. So these properties I also explained. So like first one I already talked about. So if U is harmonic and V is a harmonic conjugate of U, then minus U is a harmonic conjugate of V, that I have already explained. Then I also said that if I have a function, suppose start with the harmonic functions U, and suppose you will have two harmonic conjugate. So then what is the difference between, so how I can say that that V1 and V2, how they are differed? So the answer is that if V1 and V2 are two harmonic conjugates of U, then V1 and V2 must differ by a real constant, and that I already also explained. So what we have to do, so you say that, okay, start with the harmonic functions U. So suppose this is your harmonic functions U. Okay, so assume that V1 is a harmonic conjugate. That means you have U plus I V1. So this is analytic, right? That is by the definitions of harmonic conjugate. And suppose V2 is another harmonic conjugate of U. So therefore you have another function, say let it be F2, so that U plus I V2, that is also analytic. Okay. So therefore you have two analytic functions. So then I have to show that V1 and V2 differ by a real constant. Then what I have to do? So again consider F1 minus F2, which is exactly equal to I times V1 minus V2. Okay. So now look at the left hand side. F1 is analytic, F2 is analytic, so therefore F1 minus F2 is analytic. But now you have analytic functions, V1 minus V2 taking real value, so therefore you have analytic functions which is taking purely imaginary. Now if you remember in my earlier lectures I have proved that if I have analytic functions and if it takes either purely real or purely imaginary value, it has to be constant. So what it will implies, that means I times V1 minus V2 is exactly equal to some constant C1. So that will implies that V1 minus V2 is I times C1, which is also a constant. And then what? You can have to write just A1 plus I B1, because this is a complex number. So therefore V1 minus V2, which is taking real value, which is exactly equal to A1 and differ by a constant. So I have already explained. This one is also, you just do that. If V is a harmonic conjugate, then if I add it, then it says that this is also a harmonic conjugate. So therefore if V is a harmonic conjugate of U, then V is also a harmonic conjugate of U plus C. So that means it will not affect. So given a harmonic functions U, if I have a harmonic conjugate B, that means U plus IV is analytic. This, it says that V is also a harmonic conjugate of U plus C, because I am adding F by a constant. So if I have an analytic function, if I add by some constant, it will also be an analytic function. So therefore you can say that U plus C plus IV, which is same as U plus I times V minus IC. So therefore this is same as A. So given a functions U, okay, so V is also a harmonic conjugate. So okay, that is also okay, fine. So this is same as, yes, this is same as U plus IV plus C, that is F plus C. So therefore if F is analytic, C is a constant, so this is also an analytic function, so F plus C is analytic. So therefore this analytic function. So therefore if I have a harmonic functions. Now if U is harmonic, if I add some constant, that is also harmonic functions, right? So if I take the, it will satisfy all the conditions of harmonicity. So therefore if U is harmonic, if I add by some constant, it will also be a harmonic functions, and V is a harmonic function such that U plus C plus I times B, which is of the form A plus C, these are analytic functions. So therefore V is also a harmonic conjugate of U plus C. Third one, you just take it as an exercise and prove it. If u is harmonic and v is a harmonic conjugate of u, then this u square minus v square and uv are both harmonic functions. So that means what you have to do? You have to check that all the second order partial derivatives, they exist and it should satisfy what is called Laplace equations. And that you just do the exercise. I am not doing it here. Using the fact that u is harmonic, that means all the second order partial derivative exist and it is satisfying what is called Laplace equations. That means you have to use this kind of equations, right? Uxx plus uyy is 0, that is given, and v is a harmonic conjugate of u, that means f, if I write it, which is u plus iv, this is analytic, right? That means it should satisfy Cauchy-Riemann equations, okay? And that means you can think about that since it is an analytic functions, so therefore its derivative also analytic and so on and so forth. So if you use that kind of things and use this kind of equations, you will be able to prove that one, okay? I am not proving it, you just take it as an exercise and prove that. Number 4 also, you just take it as an exercise and prove that u, v and u square plus v square are harmonic functions in a domain D, then u and v must be constant again. So u, v and u square plus v square are harmonic functions given. That means what? It is satisfying what is called Laplace equation. So you have 3 Laplace equations you will have. Uxx plus uyy is equal to 0, vxx plus vyy is equal to 0, and u square plus v square, that is also it's satisfying what is called Laplace equation. So that means you have 3 equations. Using that, you have to show that all the partial derivatives of u, they are vanishes. That means ux, uy is equal to 0 on a domain, and your domain is nice, connected, open connected set. So therefore, u is free from x and y, and similarly you can prove for the v. So you just also take it as an exercise and prove it. 3 and 4, you just take it as an exercise. It's just using the simple Laplace equations, and you have to just do some little bit algebra. You will be able to prove 3 and 4. Fifth one, it is, I already discussed everything. Fifth one, it says that f, which is of the form u plus iv, which is analytic in a domain, then v is a harmonic conjugate, because it follows from the definition of harmonic functions. Because if f is an analytic functions, then is u and v both are harmonic functions, and v is a harmonic conjugate, that is follows from the definition, because u is harmonic and v is another harmonic function such that u plus iv is equal to f, which is analytic, that means v is a harmonic conjugate. And similarly, v is a harmonic conjugate, that is by definitions, so u plus iv is an analytic function. So therefore, this is if and only. So if I have a analytic functions f, which is of the form u plus iv, then it is if and only v is a harmonic conjugate of u. That is actually follows from the definitions. The last one is actually interesting, 6, that if I have a functions f, which is analytic in a domain, that means what? That means v is a harmonic conjugate of u. That means either you can say that this is, or you can say that this is. It is both are same. Either f is equal to u plus iv is analytic, then 5 says that v is a harmonic conjugate. So therefore, that means this is same. So that means either I can say that f is analytic or v is a harmonic conjugate. Important part is that I am assuming something more. What is that? U is also a harmonic conjugate of v. Then I have to say that f is constant, and then I also already explained this kind of things. So first of all, if v is a harmonic conjugate of u, that means f is equal to u plus iv. This is an analytic function, right? That is given first. Another hypothesis is that u is a harmonic conjugate of v. That means g, which is equal to v plus I times u, that is also analytic functions, because it is given u is a harmonic conjugate of v. That means v plus iu, let it be g, that is also analytic. So now you have 2 analytic functions f and g. Then you just do some algebra. I already explained this kind of steps, right? So what you have to do? So therefore you should say that first I am considering f plus ig. What is that? F plus ig. So if I consider f plus ig, so this should be u plus iv, okay, plus I times v minus u. So u get cancelled, so it should be actually I times 2v, okay. So now f is analytic, g is analytic, so therefore f plus ig is analytic functions. These analytic functions taking purely imaginary value. So what is that? I times 2 times v. V is taking real value, so therefore it is taking purely imaginary. So now this kind of problem I have already discussed, so therefore from there you can say that f plus ig sum c1. Do the same process, now consider f minus ig. If I do f minus ig, this should be u plus iv, okay, and this should be minus u, minus v, and then so plus u. So that means it should be this get cancelled, this should be 2u. So therefore, f minus ig, which is exactly equal to 2 times u. Now f is analytic, g is analytic, f minus g is analytic functions, which is taking purely real value. So this will implies by earlier exercise f minus ig, that is also another constant, say let it be c2. So therefore you have f plus ig c1, which is a constant. You have f plus ig is equal to f minus ig c2. That is another constant. If I add it, so therefore f is constant and similarly g is constant. So therefore f is constant, that is proved. Okay, so these are the nice properties kind of couple of properties I have listed out. Okay, there are many nice properties you will have it, and just you have to play with the definitions of harmonic conjugate using CR equations, and you will be able to prove those kind of problems. Now this is kind of informations for you, because sometimes it is like difficult to handle what is called Cartesian coordinate system. Then I can change it to polar coordinate system, and you will have the maybe that might kind of help you. Just instead of Cartesian equations, you can deal with polar equations, because sometimes it depending on what kind of functions I am giving you. So this is the one. The polar form of the Laplace equations phi xx plus phi yy is equal to 0 is given by this one. I am not proving it because this is just a change of variable formula, nothing else. So since I am changing Cartesian to polar, so what is that? X is equal to r cosine theta and y is equal to r sine theta. So therefore you just replace. So what is that? This is del 2 phi del x square plus del 2 phi del y square. This is 0. This is given, right? So you just using change of variable formula, x is equal to r cosine theta and y is equal to r sine theta, you will have this kind of equations. It will boils down to r square times del 2 phi del r square r theta. So that means r square times del 2 phi del r square at the point r theta plus r times del phi del r at the point r theta plus del 2 phi del theta square times r theta. This is 0. So this is just a change of variable. So this is the corresponding polar form of Laplace equation. Similarly, the complex form of Laplace equations phi xx plus phi yy is equal to 0 also given in this way. And what is the relations here? So here you can have x is equal to z plus z bar by 2 and y is equal to z minus z bar by 2y. Again, do the same. Just makes you have a xy variable equations, you change it to another variable z and z bar, and it turns out that your Laplace equation turns out to be this one. This is the polar form and this is the complex form. So as I said, sometimes it is very difficult depending on the functions, what kind of functions I am giving you, to check whether it is satisfying Laplace equations or not. Sometimes it will be useful if I change it to polar coordinate or if I change it to complex form, like to handle those kind of functions in terms of polar form might be useful or in terms of complex form might be useful. That time you have to use this kind of equation to check that your functions satisfying what is called Laplace equations. This is the corresponding Laplace equations form in polar form and in complex form. So this is the last one. So this is like a bit about what is called, I have already discussed harmonic functions and these things. Now as I said, so analytic point I have discussed, a function is analytic. So now this is the like singular points or singularities. So more about singularities I will talk about later when I will introduce the notions of what is called power series. So power series, then you will have a Lorentz series, so there we will have more about the singularities. But just to give a kind of definitions of singular points or singularities, so I will have these definitions. So singular point you can think about it is a negations of analytic point. So what is that? Kind of say the definitions. So of course it is like a function is not analytic means the function actually that point is a singular point, but it will have something more. What is that? Look. So definition, a point z0 is said to be a singular point of my functions f if fz is not analytic. Okay, so therefore if my function is not analytic, that means it is singular. Then I will have some extra conditions. What is that? You see, first of all, f is not analytic at a point. Of course it has to be like that. Then every neighborhood of nz0 of the point z0 contains at least one point where my function is analytic. That means I am demanding little more. So what is the meaning of analyticity at a point? So if I talk about say analyticity at a point z0, if you remember, I defined that analyticity at a point means there exists a neighborhood at each point my function should be differentiable, right? Now what is the definition of singular point? A point is called a singular point, that means it is not analytic. So what is the negation statement of that? That means whatever neighborhood I can take at the point z0, I should have at least one point where my function is not differentiable. That is a meaning that my function is not analytic, right? So therefore, no analytic at a point z0 means there exists a neighborhood such that at each point my function should be differentiable. So my function is not analytic. That means whatever neighborhood I can take around the point z0, there should exist one point where my function is not differentiable. That is plus something. What is that plus? It says that again every neighborhood of nz0 of the point z0 contains at least one point such that my function is analytic. That means it says that yes. So that means whatever neighborhood I can take, well, it is fine that at least one point my function should not be differentiable. That is okay. On top of that, I want that there should exist another point where my function is analytic. That means in that point there exists a neighborhood where my function should be differentiable. That means it will little bit more than the negations of analytic at a point. So of course I say that my function the point z0 is a singular point of my functions f if my function is not analytic at the point z0, and whatever neighborhood of z0 I can take, it should contain at least one point where my function is analytic. See, at least one point. That means it is not just the negation of what is called analyticity at the point, but it is something more. Of course, my function should not be analytic at that point. On top of that, I want that every neighborhood of that point should contain at least one point where my function is analytic. Okay, if I talk about example, it will be more clear. For example, okay, if these things happen, then I am saying that my function has a singularity at the point z is equal to z0. For example, you just consider this function f of z is equal to 1 by z minus 1. Now what kind of functions? Of course this function is very nice functions, but at the point 1 it will have some kind of problems, because at the point 1, so z minus 1 is the denominator, so it will blow up. So if z approaches to 1, the functions blow up. Okay, so that means at the point 1 you can guess it will have some singularities. Now look, so this is your complex plane, so this is my point 1 comma 0, right? Now I'm saying that according to my definition, this is a singular point. Why? Because if this is my point 1, now whatever neighborhood I can take around the point 1, whatever neighborhood. So two things it should be there. First of all, my function should not be analytic at the point 1, and whatever neighborhood I can take, at least one point I should have, so that my function should be analytic. Now you see, whatever neighborhood I can take around the point 1, this neighborhood contains the point 1 itself, and at the point 1 my function is not differentiable. So that means my function is not analytic at the point 1. That is one. And not only that, if I remove the point 1, at any other point my function is perfectly alright. My function is differentiable. So therefore if I take a point here, so and this around this point, my function is perfectly alright, because it is away from 1. So this function is like quotients of two polynomials, so therefore my function is what is called no singularities in this neighborhood. My function is differentiable, therefore it is analytic. So therefore the functions f of z, which is exactly equal to 1 by z minus 1, whatever neighborhood I can take around the point 1, it contains the point 1 where my function is not differentiable. That means my function is not analytic. Not only that, whatever neighborhood I can take, whatever neighborhood you can take, if I remove the point 1, at each point my function is perfectly alright. That means at each point my function is differentiable. So therefore if I take here point here I will get a small open neighborhood, or at each point my function is differentiable. So therefore I will have the existence of a point where my function is analytic. So therefore it satisfies this definition. So therefore 1 is a singular point. Similarly, I have given this example, f of z is equal to 1 by z minus 1 times z minus 2. So here you will have two kind of disturbing points you will have. One is 1, another is 2. So 2 comma 0, this is 1 comma 0. These functions 1 and 2 are the singular points. Again you can do the same argument, because if I take whatever neighborhood I can take, whatever neighborhood, doesn't matter. Okay, so at least one point should inside that neighborhood, so where my function is not differentiable. So therefore at the point 1 my function is not analytic, and if I remove this point, at least you have some another point where at each point in that neighborhood my function should be differentiable. That means I have the existence of at least one analytic point near the point 1. So therefore this one point is a singular point, and similarly you can go for 2. So this is the example of singular points. One observation, the polynomials has no singular points. Polynomial functions are nice functions actually. Okay, this is another definition. Later on I will use it. So I will say that a functions f from c to c, it is defined on whole complex plane, is said to be an entire functions if my function is analytic at all points on the complex plane. So a functions f from c to c, it is called an entire function if my functions is analytic at all points. For example, polynomials. So polynomials are entire functions. So later on you will see, so instead of polynomials, can I have some other functions different from polynomials? Still I can talk about that my function is analytic everywhere, or entire functions. Answer is yes, there are many functions. For example, one easy function is the exponential functions. So like for example in real analysis, you know, exponential functions is infinitely many times differentiable. So therefore you will see later on when I will talk about exponential functions, then you will see it satisfies all the properties of analyticity, and it is analytic at each point, and therefore it is at each point in the complex plane, so therefore it is an entire function. So this is the first non-trivial examples apart from polynomials which are also entire functions. Okay, so I think that's all for week 2 lectures. So I think in my next week I will start about what is called multi-valued functions, and then I'll talk about the branch. But before that, I need to talk about little bit about elementary functions, like the functions you know, what is called sine function, cosine function, exponential functions. In the real valued functions of real variable, you know. Similarly, I can have the kind of notions of sine function, cosine functions, and exponential functions in the context of complex valued functions of complex variables. So I'll start with that. Then you'll have, of course, the notions of logarithmic functions, and there I'll talk about that it is actually a multi-valued functions, and out of that you will have a single valued functions, and so on and so forth. So I think in my next week I will start with the what is called multi-valued function. In fact, I should say that elementary functions, and then I'll start with multi-valued functions and its branch. Okay, so I think for the timing I should stop here. In my next lecture I will start with elementary functions. Thank you.